Control of a dynamical system requires that the system state remain at positive distance from the failure boundary at the moment the control action is applied. This distance is called structural slack. It is the minimum distance from the current state to the absorbing set, measured in the geometry of the state space. When structural slack is 0, the system is on the failure boundary. At that point, no control policy can redirect the trajectory. Absorption is immediate and certain. Structural slack is not a behavioral property of the control policy. It is a structural property of the state and the state space geometry. It must be maintained as a prerequisite, not recovered after the fact. The state space of a controlled system is partitioned into the feasible set and the absorbing set. The feasible set is the region where the system is live. Transitions occur, control is applicable, and trajectory behavior is determined by the transition kernel. The absorbing set is the failure boundary. Once entered, no further transitions occur and all control authority is lost. The stopping time is the first hitting time of the absorbing set. It marks the irreversible transition from feasible to absorbed. System architecture must specify the geometry of both sets explicitly. The shape of the feasible set determines which states have positive slack, and therefore which states are candidates for effective control action. The feasibility boundary separates states where control is effective from states where it is not. A state is feasible if and only if its distance to the absorbing set is strictly positive. Structural slack is non-zero. The feasibility boundary is the set of states at exactly 0 slack, the last reachable layer before absorption. Systems operating near the feasibility boundary are at maximum fragility. Small perturbations in the state process cross into the absorbing set with high probability. Architecture decisions that reduce the feasible set, increase the absorbing set, or allow the system to approach the boundary without a recovery mechanism all increase the probability of premature absorption. The boundary geometry is a formal architectural parameter, not an incidental feature. Structural slack is defined as the infimum of distances from the current state to the absorbing set. Positive slack is a necessary condition for any control to be effective. It is not sufficient, but it is prerequisite. When slack reaches 0, the system is absorbed with probability 1 at the next transition. No policy can recover this. Slack is structural because it depends on the geometry of the state space, not on the policy applied. A policy can consume slack by driving the system toward the boundary, but no policy can create slack from 0. This asymmetry is fundamental. Slack is depleted by operation and restored only by architectural intervention that expands the feasible set or contracts the absorbing set. A controlled transition kernel is defined only for states where structural slack is strictly positive. As slack decreases toward 0, the absorption probability under any policy increases toward 1. No policy can stabilize a system whose state is already on the failure boundary. There is no controlled kernel defined at that point. Control policies are therefore functions on the interior of the feasible set, not on its boundary. The practical consequence is that system designers cannot rely on control policies to compensate for insufficient slack at the architecture level. Slack must be maintained by design through the choice of state space geometry, transition rate parameters, and recovery mechanisms before any policy is applied. 3 canonical examples illustrate the structural slack requirement. A queuing system operating at capacity, arrival rate equals service rate, has no slack in the throughput dimension. Any perturbation triggers unbounded queue growth. A thermal reactor at its design temperature limit has no thermal slack. Control rods can slow the reaction, but cannot remove heat already accumulated. A financial system with 0 reserve buffer has no capital slack. Regulatory control instruments become structurally inoperable. In each case, the control architecture is formally valid but operationally void. The system reached a state where the controlled kernel is undefined. Structural slack is not a design preference. It is the precondition for control to exist.